creating quadratics from graphs, okay? So, like we just said, we took a picture, or we found a picture on the internet of Nathan's Phillips square, and we superimposed our coordinate grid above it. What we're going to do is we're going to put in some numbers, and I think maybe this color might show the best. This is 1, 2, 3. I'm going to go by 2's on the other side. So -2, -4, -6, -8, -10. And we'll do the same thing up. So we've created our graph above. This is super hard to see. -6, 8, 10. Good. Okay. And what we're going to do is we're going to use a different method for each arch to essentially figure out what shape it is and what equation would represent it. So we want to kind of highlight what we have here. I'm going to try to use something that'll stand out. I'll try to trace over this. Okay, so here's essentially our parabola. Okay, kind of hard to see. But what's really important here is we want to find out some coordinates. And I'm going to go on the assumption that this is roughly where the vertex is, okay? So I probably should have not drawn that in. Probably wouldn't be easier to see. But we're going to make an assumption of where the vertex of this is. So we're going to call this the vertex at this point. And this point on our graph is when x is -2. So we have an x value of -2. And we have a y value of roughly 3. Okay? So here's a y value. And that's a pretty good estimate of where the vertex of this one is. So right now what we're going to do is we're going to use vertex form to figure out the equation of this. Okay, so if you guys recall from our vertex form, we take our vertex here, and we know that this is actually the h and k value. I think we did h, this, and our k. So if you guys recall, vertex form is written as y is equal to a multiplied by x minus h squared plus k. And this is when we were transforming quadratics. This is back in one of our other chapters. Okay? And this might be one of the easiest ways to do stuff. So, if you guys recall, we said that our h and k are actually the x and y values of our vertex. And this is where we estimated the vertex of this shape to be. So our h is -2 and our k is 3. So we're going to plug in those values. So we have y is equal to a x, and then it's minus, and h is technically -2, okay? So it's minus -2, which is very important, hence why we'll end up getting our opposite sign. And our k value was +3. So remember, our h values were always opposite. If you look, y equals a x, what did the two negatives become? That's right, so +2, right? And that's why we kind of get that relationship where +2 inside vertex form is going to the left 2 units, okay? And then we have our +3. So we've already fulfilled h and k, 2 of the variables. The only one we don't know is our a. We don't know the a, so instead what this is stretched by, okay? And I guess it would have been a little nicer. I'm going to erase some of this to find a really good point here, okay? That was our estimate of our vertex. We just have to find another point along this graph, okay? So I'm going to look for a point that's probably pretty easy to use. This looks like a very definitive point here, okay? This point here is when x is -8 and our y value is 2. Okay? So these represent an x and a y. So this is very important because we have to figure out a. And in order to isolate for a variable, we need to put in values for all the other variables. Well, h and k are done, and the last one we have to find is a. So we need coordinates for x and y, which we have here, x at -8 and y at 2. So we're actually going to replace our x value with -8 and our y value with the value of 2. And that way we'll be able to isolate for our a. So what is stretched or compressed by? So we said y was 2 is equal to a. X is -8 plus 2 squared plus 3. Now the only variable left is a. So we can isolate for our a. So we go through BEDMAS. What's -8 plus 2? Right? So we have -6. It'll be squared. What's -6 squared? Okay. And when we multiply it by a, we usually write it in the form of 36a, right? Plus 3. The goal is to isolate a, so when I bring 3 over, what does it become? Okay. So 2 minus 3 is equal to 36a. This becomes negative 1 is equal to 36a. And how do we isolate a? All right, we divide both sides by 36. And we'll leave it as a fraction. What is our a value? Negative 1 over 36. So the equation, oops. Okay, remember this was our equation here minus the a, is y is equal to negative 1 over 36, x plus 2 squared plus 3, which actually makes a lot of sense because our parabola, let's zoom out just a little, maybe a little more. That was the wrong button. There we go. Our parabola, which way was it facing? Was it opening up or down? So it has a maximum, so it was facing down, so a value is negative. That makes sense. And does it look like it's very stretched, or is it very compressed? Very compressed. So it's between 0 and 1. And this is a value that's very close to 0. The closer we get to 0, the wider the parabola is. So we have negative 1 over 36. You could put it as a decimal. It would be a really small decimal in that place. Okay? But this is essentially the equation using our vertex form. Okay, so we've done that idea. We did the parabola on top. That's the top one. The second one we want to work with is this one below. And I want to use a different form. I actually want to use factored form for this. Okay? Now, factored form deals with what? What are the key points in factored form? What does it help us find? The zeros, the x-intercepts. So let's try to estimate what the x-intercepts of this parabola are. We're going to say this is at 2, one of them, and the other one, negative 8. I'm going to estimate using whole numbers. It's very possible that it's at a decimal, but it'll be harder for us to work with those numbers. Okay? So these are our R and S, you could say. So let's go into our factored form. Scroll down a little and give me some room here. So our factored form, if you remember, is f at x, or y, is equal to a times x minus r, x minus s. And our r and s were at a value of 2 and a value of negative 8. So what we're going to do is we're going to take these values and replace our r and s. And it didn't matter which represented which one. Okay? So f at x or y, I'm going to write it as y this time, both meaning the same thing. We have a, x minus a value of 2, and an x minus negative 8. Okay? When we simplify that bracket on the right, what does it become? Yeah, there we go. X plus 8, which leads us to that conclusion where it tends to be the opposite number as long as there's a value of 1 in front of the x. We tend to have opposites in those factored forms. That's what our x-intercepts are. So we've replaced them. And in the same thing that we did with our vertex form, we still have to find our value of a. So what other piece of information do I need from this parabola to help us find our a? It doesn't have to be the vertex. Any point along. So let's find any point. And I can actually go down here and find a point. This looks like it's at 6 and negative 2. I think that is. This point looks like it's at 6 and negative 2. So we're going to say 6 and negative 2 as another coordinate along here. So as our x and our y. So let's go way down to our factored form. 6 and negative 2. We're going to replace our x and y values. So there are 2 x values here and 1 y value. We're going to replace y with negative 2 is equal to a times, and our x's are the number 6. So 6 minus 2 and 6 plus 8. Now there's only one variable left, which is the letter a, which is great because that's what we need to find. So we have negative 2 is equal to, we simplify this bracket, this becomes 4. Over here we get 14. Who can help me out with what 4 times 14 is? Anyone know? I think it's 56. Good. In order to isolate a, we divide both sides by 56. So we get a is equal to negative 2 over 56, and that can actually be reduced to 1 over 28. 28, that's right. 1 over 28. And of course, it's negative. So back to our factored form here. let's put it all in. Y is equal to, we take our a, which is negative 1 over 28, and we have x minus 2, x plus 8. And that's the equation of the second parabola we've drawn. So we've now drawn two parabolas. And that makes sense. It's negative, so it's facing downwards. And it's relatively compressed also. So let's put it into our Desmos program. Try to remember that off the top of our head. We already have our first one. Let's see if the relationship looks somewhat similar. Negative 1 over 28. And we have x minus 2, was it? And x plus 8. And if you see from their relationship, that looks pretty similar to what our picture was. Our picture had, let's scroll up to see it. Our arches at Nathan Phillips Square having roughly that type of relationship. The one inside looking like it's a little more stretched, and the one on top looking like it's a little more compressed, is exactly the same idea we have here. The blue one looks a little more stretched, and the red one a little more compressed.